friends, welcome to our YouTube channel Naraj Academy. The main aim of this lecture is to discuss about the communication systems prelims questions of the ESE of previous year in a very detailed manner. And if you like the content of our channel, then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button so whenever we upload a new video, the direct notification comes on mobile. If any improvements needed in our lectures, then please do comment in the comment section. We will definitely include all those improvements in the coming lectures. So why to waste more time? So let's get started. So now we are going to solve the 131 question. See the question here. For a non-uniform quantizer, more quantizing steps are used for signals of. So what are the four options? Option B, high amplitude. So here for non-uniform quantizer, more quantizing steps are used for the high amplitude signals. So let's solve this numerical. So this is a graph of the channel noise. So from minus delta by 2 to delta by 2, its value will be 1 by delta, means area is equal to unity. So quantization noise power is equal to mean square value, means we have to find what is the expectation of the x square, which is integration of minus m to plus m to x square f of x dx. As this function is defined only from minus delta by 2 to delta by 2 and remaining all other instants, its value is 0. So therefore this integration is going to converge from minus delta by 2 to delta by 2 x square into 1 by delta dx. So if you do the integration and if you substitute the limits, finally we are going to get the quantization noise power is equal to delta square by 12. So therefore quantization noise power is equal to delta square by 12, where delta is called as a step size. So if you see carefully, as the amplitude increases, as the signal amplitude increases, means here as the amplitude increases, the power is also going to increase. So therefore quantization noise power is also going to increase. So as quantization noise power increases, so delta value is also increases. So we can conclude that here the large step size are required for the high amplitude signals. So therefore in non-uniform quantizer, more quantization steps are used for the high amplitude signals. So therefore here high quantization steps are required for the high amplitude signals. And do the reverse one. See, as the amplitude decreases, then quantization noise power decreases, and also this delta value also goes on decreases. So we can conclude that low amplitude signal requires low step size. So we can conclude that in non-uniform quantizer, less quantization steps are required for the low amplitude signals. So we can conclude that as the amplitude increases, we need higher and higher stepper values. We need more step size values, and if the amplitude value decreases, then we need less number of the step values, or the less number of the quantization steps values we need to require. So in this question they ask what is value if delta is increases, means if the delta is increases means the quantization noise power increases for the high amplitude signals only. So now we are going to solve the 132 question. So the question here, in a PCM system, each quantization level is encoded into 8 bits. The signal to quantization ratio is equal to. So in this question the number of bits is 8 bits, means for each and every sample the number of bits is 8. So in the PCM, so now we need to find what is the signal to quantization noise ratio. We need to figure out in the terms of the dB value. We need to figure out. So what are the four options? Option B, 48 dB is the correct solution of this question. So let's solve this numerical. So signal to quantization noise ratio in PCM is 1.5 into 2 to the power of 2n. So let me derive this formula also. See, the message signal m of t is equal to, let me assume the message signal, the waveform is Vm cos 2 pi fmt. So I want to calculate what is the range of this message signal, means maximum peak value minus minimum peak value of the message signal. Maximum peak value is plus Vm and the minimum peak value of this message signal is minus Vm. So Vm minus of minus Vm is 2 Vm, the range of the signal. And the power in the message signal is nothing but RMS value whole square. RMS is Vm by root 2 whole square, which is Vm square by 2. This is the signal power. This is this much amount of power which is present in the signal m of t. And the quantization noise power just now approved in the previous example, which is delta square by 12. So therefore delta is nothing but the step size is equal to R range by L. So R we have known just now, which is 2 Vm by L is equal to the power of n. So therefore here I have already told you the signal to quantization noise ratio is nothing but signal power by noise power. Signal power is nothing but Vm square by 2 and the noise power is delta square by 12. So we know the value of delta. So substitute the delta value 2 Vm by 2 to the power of n, and you do this calculation, finally we are going to get 1.5 into 2 to the power of 2n. So therefore signal to quantization noise ratio in PCM is 1.5 into 2 to the power of 2n. So now I want to convert this into dB. So therefore dB 10 log base 10. So now this value I have to keep here, this SNR. So here this value I have to keep here, which is 1.5 into 2 to the power of 2n. So after solving this one, finally we are going to get, which is SNR in dB 6n plus 1.76. So I am going to approximate this 1.76 to 1.8. So therefore this is the approximate equation. So therefore in the question they are given the number of bits for each and every sample, which is 8. So therefore in place of n I am going to substitute 8. 6 8s are 48 plus 1.8, which is 49.76 accurate value. But in the options they have given only 48. So therefore we have to approximate this to 48. So therefore, but the accurate answer is 49.76, but the approximate answer is in the options only option B is nearest to 49. So therefore 48 dB is the correct solution of this question. So now we are going to solve the 133 question. See the question here. 4 signals, each band limited to 5 kHz, are sampled at twice the Nyquist rate. The resulting pulse amplitude modulation samples are transmitted over a single channel of the time division multiplexing. The theoretical minimum transmission bandwidth of the channel should be. So in this question they are given a 4 signals of each having the maximum message signal frequency is 5 kHz, and they are now doing a sampling at twice the Nyquist frequency, and they're asking what is the minimum bandwidth is required. So what are the 4 options? Option B, 20 kHz is the correct solution of this question. So let's solve this numerical. So in the question they are given 4 signals. I am going to assume G1 of t, G2 of t, G3 of t and G4 of t are the 4 signals with the maximum message signal, which is 5 kHz for each and everything. So in the question they are given that here minimum sampling frequency is nothing but it is called as a Nyquist frequency, which is twice the message signal frequency. So you have to multiply by 2. So therefore find the 2 is 10 for each and everything. But here in this question they are sampling twice the Nyquist frequency. So the sampling is done at the twice the Nyquist frequency, means minimum frequency. So you have to go for the again twice. So therefore 10 into 2 is 20. So 20 kHz for each and everything. So this sample is sampled with 20 kHz. So each and every 4 signals are sampled with the 20 kHz. So now I want to know what is the overall sampling rate, means we have to add each and every sampling frequency value. So therefore 20 plus 20 plus 20 plus 20, which is 80 kHz. So now I want to know what is the bandwidth of this one. So bandwidth is equal to total sampling rate by 2. So therefore 80 by 2 is nothing but 40 kHz. But this is not the minimum bandwidth. This is the bandwidth for this sampling rate. But here in the question they asked what is the minimum bandwidth. So in order to have a minimum bandwidth, the total sampling rate should be also minimum value. So therefore if you want to know what is the minimum total sampling rate, you have to go for the minimum sampling frequency, means the Nyquist frequency itself, but not the twice the Nyquist frequency. So if the question, if they asked for twice the Nyquist frequency, what is the bandwidth, means this is the answer. But in the question they asked what is the minimum bandwidth, means we have to go for the minimum sampling frequency, means this value we have to go. So therefore total sampling rate minimum value. So therefore minimum frequency, sampling frequency we have to go for each and every signal, which is 10 kHz for each and every signal. So therefore 10 plus 10 plus 10 plus 10, which is 40 kHz. So therefore minimum bandwidth is equal to total sampling rate minimum by 2. So therefore 40 by 2 is nothing but 20 kHz. So therefore this is the correct solution of this question. So therefore here always you have to remember here, if you want to know what is the minimum bandwidth, then you have to take the total sampling rate of minimum value. But in the question if they ask what is the bandwidth for this twice the Nyquist frequency, means this is the correct solution. But in the question they asked what is the minimum bandwidth, means this is the correct solution of this question, which is 20 kHz. Then we have to go for the total sampling rate of the minimum value. It occurs only for the minimum sampling frequency of each and every signal. So 20 kHz is the correct solution of this question. So now we are going to solve the 134 question. See the question here. A continuous signal has a voltage range from minus 2 volt to plus 2 volt. If this is contacts to 8 bits, what does the resulting signal have? So therefore in the question they are given a message signal. It is going to have a peak and minus peak value, means negative peak value and the positive peak value of plus 2 volt and minus 2 volt, and the number of bits is 8 bits. So here the resulting signal, what does it have? So what are the 4 options? 8 bits per sample if properly good. 8 bits per sample if properly sampled. So let's solve this numerical. So in the question they are given that For each and every sample, the number of bits is 8, and also they given the maximum peak voltage and the minimum peak voltage also they are given. So therefore, in order to calculate what is the range of the message signal, Vmax minus V minimum. Vmax is 2 volt and V minimum is minus 2. So we are going to get range is equal to 4 volt, which is the peak to peak voltage of the message signal. So therefore delta is called as the step size, which is range by L. So range is 4 and the number of levels is 2 to the power of n. So therefore here n is equal to 8. So therefore 4 by 2 to the power of 8 is 4 by 256. So we can conclude that the levels is equal to 2 to the power of n. So in place of n substitute 8. So 2 to the power of n is equal to 256, means 256 numbers of standard levels are possible with the n is equal to 8 bits for each and every sample. So step size is nothing but 4 by 256. So if you see the option A, they are given that 255 levels, but here we are going to get 256 levels. So option A is wrong, and the option B is 25 levels. So but here the number of levels is 256. So option B is also wrong, and option C, they are given 8 bits plus 2 levels at minus 2 and plus 2 volts. See here, with 8 bits we can only get here 256 levels. We can't get more than 256. This is the maximum limit. So option C is also wrong. So therefore option D is the only thing which is remain, which is 8 bits per sample if properly sampled. So therefore 8 bits per sample if properly sampled means if you do the sampling at properly with the minimum sampling frequency, then each and every sample is going to represented by 8 bits with the number of levels is 256 and the step size is 4 by 256. So this is the correct solution of this question. So now we are going to solve the 135 question. This is the most fascinating question. So see the question here. The peak to peak input to an 8-bit PCM coder is 2 volt. The signal power to quantization noise power ratio in dB for an input of 0.5 cos omega mt is. So in this question here, they are given the first signal is which is going to have a peak to peak voltage of 2 volts for 8-bit PCM. So there is another new signal which is 0.5 cos omega mt. For this signal we need to find what is the signal power to quantization noise power in dB we need to figure out. So what are the four options? Option B 43.8 is the correct solution of this question. So let's solve this numerical. So for this PCM the number of bits per sample is 8. So for the first case here, the message signal has a peak value of 2 volts they have given. So therefore this is the signal I am going to assume the positive peak value 1 and the negative peak value of minus 1. So the range is equal to positive peak value minus negative peak value. So positive peak value is 1 minus of negative peak value is minus 1. So 1 minus of minus 1 is nothing but 2, which is called as the peak to peak voltage of the message signal. And I want to know what is the power in this message signal, because it is a periodic signal which is RMS whole square. The RMS is Vm by root 2 whole square, which is Vm square by 2. The peak value is 1 volt. So 1 square by 2, which is 1 by 2. This is the power. This is a power which is present here. We can also say it as a signal power. So therefore here signal to quantization noise ratio, which is already I have told you, which is 1.5 into 2 to the power of 2n. So therefore here this is called as is equal to signal power by noise power. I have already told this one, signal power by noise power. So therefore here I want to convert this into dB value. So if I want to convert this into dB value, because it's the first case, so I am going to keep it here 1. So if you want to convert into dB value, so 10 log base 10 of SNR. So SNR is equal to this value you have to keep here. Then finally we are going to get 6n plus 1.8 here. So here n is the number of bits per sample, which is already 8 in the question they are given. So 6 8 is 48 plus 1.8. So therefore finally we are going to get signal power to quantization noise power in the first case for this signal, which is 49.8 dB. So now for the second one we have to figure out. So therefore here this is the message signal m of t 0.5 cos omega mt. So this is the diagram here. Positive peak value 0.5, negative peak value minus 0.5. So I want to know what is this range of this signal, means peak to peak voltage. So which is maximum voltage minus minimum voltage value, which is 0.5 minus of minus 0.5, which is 1, which is also called as a peak to peak voltage of this message signal. So what is the power in this signal, which is Vm by root 2 whole square, means RMS voltage whole square. RMS is Vm by root 2 whole square, which is Vm square by 2. So Vm Positive peak value is 0.5. So 0.5 whole square by 2, which is nothing but 1 by 8. So therefore here I have already told you signal power to noise quantization power is equal to signal power by noise power. So noise power is independent of the type of the signal. So we can conclude that here the whatever the noise power in the first case is also equal to noise power in the second case. But as the message, as the signals are varying, the signal power is also going to vary. So therefore here S1 by N1, this is S2 by N1, because here N2 and N1 are equal, because N1 or N2 are the noise power is independent of the type of the message signal. So therefore here N1 is equal to N2. So I want to do the ratio of this one, SNR1 by SNR2. I want to do the ratio. So SNR1 by SNR2. So therefore S1 by N1 by S2 by N2. So N1 N2 get cancelled. So we are going to get S1 by S2. S1 is called as the signal power in the first signal, and S2 is called as the signal power in the second signal. So the power in the first signal is half and the power in the second signal is 1 by 8. So if you do the calculation, we are going to get 4. So therefore signal to quantization noise ratio in the first signal is equal to 4 times of the signal to quantization noise power in the second case. So now I am going to apply 10 log base 10. 10 log base 10 for each and everything. So therefore here 10 log base 10 is equal to, in place of SNR1 I am going to keep here 4 SNR2. So 10 log 10 in place of SNR1 4 SNR2. So therefore log m into n is equal to log m plus log n. So therefore 10 log base 10 4 plus 10 log base 10 SNR2. So if you see carefully, this value we already know. This is the dB value. So this is a dB value which is 49.8. So therefore this is the 14.8. 10 log base 10 4 is nothing but 6 value, 6 dB. This is 14.8 dB and this is 6 dB. This is 10 log base 10 SNR2 is called as the dB value of the SNR of the second signal, which is SNR2 dB. So therefore SNR2 dB if you want required, so 14.8 minus 6, which is SNR2 in dB value, which is 49.8 minus 6 is 43.8 dB. So therefore this is the correct solution of this question. So now we are going to solve the 136 question. See the question here: a sinusoidal signal with peak to peak amplitude of 1.536 volt is quantized into 128 levels using a mid-rise uniform quantizer. The quantization noise power is. So in this question they are given a peak to peak voltage of the signal, which is 1.536 volt, and the number of levels in this are 128 levels. So we have to find, based on this we have to find what is the quantization noise power we need to figure out. So what are the 4 options? Option C, 12 into 10 to the power of minus 6 volts square is the correct solution of this question. So let's solve this numerical. So here in this question the range is equal to maximum voltage minus minimum voltage, which is called as the peak to peak voltage of the message signal. This value they already given in the question, which is 1.536, and also the number of levels used in this also they have given, which is 128. Always the number of levels should be always less than or equal to 2 to the power of n. So based on these two data we need to find what is the quantization noise power. So therefore L is equal to 128 less than or equal to 2 to the power of n. So 128 means 2 to the power of 7 less than or equal to 2 to the power of n. So based on this we can tell that for each and every sample the number of bits required is 7. So therefore here delta is called as the step size, which is R by L, range by total number of levels. Range value we know, which is 1.536, and the number of levels is 128. See here, if we want to know what is the unit of this delta, see the range, the unit of the range is volt and the unit of L is unitless. So therefore the unit of this delta is called as the volt. So therefore quantization noise for this formula just now discussed here, delta square by 12. So whatever the delta value, keep here and do the square and do the divide by 12. Finally we are going to get 12 into 10 to the power of minus 6. See here, QNP, quantization noise power, is called delta square, so volt square. So therefore the unit of the QNP is called as the volt square. So this is the correct solution of this question. So now we are going to solve the 137th question. See the question here: a signal is sampled at 8 kHz and is quantized using 8-bit uniform quantizer. Assuming signal to noise ratio, quantization noise ratio for a sinusoidal signal, the correct statement for PCM signal with a bit rate of R is. So in this question they are given a it is sampled at, means sampling frequency they are given 8 kilohertz, and the number of bits which are used in this PCM is 8. So we have to find what is the SNRQ, and also we have to know what is the bit rate we need to figure out. These two things we need to figure out. So what are the four options? Option B is the correct solution of this question. The bit rate is 64 kbps and the signal power to condensation noise power is called as a 49.8 dB. So let's solve this numerical. So in the question they are given that the sampling frequency is 8 kilohertz and the number of bits per sample is 8 bits. So we have to find what is the bit rate, and also we have to find what is the signal power to condensation noise power in dB we have to figure out. So therefore bit rate is equal to n into fs. So the n is nothing but 8 and fs is 8. So 8 into 8 is called to 64 kbps. Means this much amount of bits per second are being transferred. And also SNR in dB. So we have just now derived this formula also, which is 6n plus 1.8. This is only for the assuming that the message signal is a sinusoidal nature. Then only this is the correct value. If any other signal, then this is not the correct formula. So therefore here in the question also they are asking that the message signal is a sinusoidal signal. So the formula is 6n plus 1.8 dB. So we know the value of n, which is 8. So substitute here 6 into 8 plus 1.8, which is 49.8 dB is the SNR dB. So therefore finally the bit rate is 64 kbps and the SNR dB is 49.8 dB. So now we are going to solve the 138 question. See the question here. 4 message band limited to omega, omega, 2 omega and 3 omega respectively are to be multiplexed using TDM, time division multiplexing. The minimum bandwidth required for the transmission of this time division multiplexing signal is. So we have to find what is the minimum bandwidth with the help of the TDM principle. So what are the four options? Option D 7 omega is the correct solution of this question. So let's solve this numerical. So there are 4 signals, G1 of t, G2 of t, G3 of t and G4 of t. The bandwidth means the maximum message signal can possible is omega, omega, 2 omega and 3 omega. So therefore here in the question they are asking what is the minimum bandwidth by using the TDM, time division multiplexing. So therefore the sampling frequency has to be minimum, then only the bandwidth will be minimum. So therefore it is twice the message signal frequency. So therefore 2 into bandwidth. So you have to go for the twice of each and everything. So 2 omega, 2 omega, 4 omega and 6 omega. So this is we are going to get. What is the total sampling rate? So total sampling rate is also called as the overall sampling rate. So we have to add each and every minimum sampling frequency we have to add. So 2 omega plus 2 omega plus 4 omega plus 6 omega, which is 14 omega. So now I want to know what is the minimum bandwidth, means minimum total sampling rate by 2. So therefore 14 omega by 2 it is called as a 7 omega. So here if the total sampling rate is minimum, the bandwidth is also minimum. So total sampling rate will be minimum only if you are going for the Nyquist frequency or the minimum sampling frequency for each and every signal, then only the minimum bandwidth is going to occur. The solution is 7 omega. So now we are going to solve the 139 question. See the question here. The bandwidth of a PCM system having 2 condensation levels is B. If the condensation levels is increased to 8, the resultant bandwidth will be. So in this question here, if the number of levels is 2, then the bandwidth is B. Then if the number of levels is 8, then what is the bandwidth they are going to ask here. So what are the 4 options? Option C 3B is the correct solution of this question. So let's solve this numerical. So here the bandwidth of the PCM is going to lie between the half of the bit rate and the bit rate. So here I am going to assume the minimum bandwidth of the PCM. You can go for the either RB also maximum, still the answer will be same. So therefore here the minimum bandwidth of the PCM I am going to assume which is half of the bit rate. So half of the bit rate is nothing but bit rate means n into fs by 2. So therefore here in the first case the number of levels is 2. So always the number of levels is less or equal to 2 to the power of n. So levels is 2 means 2 less or equal to 2 to the power of n. So by comparing here n is equal to 1 means with the help of 1 bit we can get 2 levels. So therefore here the bandwidth is equal to here n into fs by 2. So n is equal to 1. So 1 into fs by 2. In the question they also given that the bandwidth for the first case is b. So therefore b is equal to fs by 2. So for the second case if the number of levels is 8, so therefore number of levels always less than or equal to the power of n. In the term of L you have to replace 8 less than or equal to the power of n. So 8 is nothing but 2 cube. So therefore by comparing both of them we are going to get here 3. So with the help of 3 bits we can get 8 levels. Up to 8 levels is possible. So therefore here the bandwidth in this case is equal to, in place of n substitute 3, so 3 fs by 2, but already we know which is fs by 2 is nothing but b, so therefore 3 into b. So as the levels is increased from 2 to 8, the bandwidth is thrice the previous bandwidth, which is 3 times the bandwidth. This means as the levels is increases, the number of bits are also increases, so therefore the bandwidth also going to increase. So this is the correct solution of this question. So this is the last question of this lecture. See the question here. Analog data having highest harmonic at 30 kHz generated by a sensor has been digitized using 6-level PCM. So what will be the rate of digital signal generated? So here they are given a maximum message signal frequency is 30 kHz, and also they are given that in this PCM the number of standard levels are 6. So based on these two, we need to find what is the bit rate. The bit rate we need to figure out. So what are the four options? Option D, 180 kilobits per second is the correct solution of this question. So let's solve this numerical. So in the question they are given that the message signal maximum frequency allowed is 30 kHz, and also the number of levels used is 6. So therefore we know here the number of levels always less than or equal to 2 to the power of n. So here 6 less than or equal to 2 to the power of n. See, if you see here, if n is equal to 1, we only get the 2 levels. 2 to the power of n is 2. So therefore if n is equal to 2, we are going to get here 2 to the power of 2, which is 4. Only 4 levels are possible. When n is equal to 3, we are going to get 2 cube means 8 levels. So 6 is going to lie between the 4 to 6. So therefore minimum 3 bits are required. Minimum 3 bits are required in order to get a 8 levels, means 6 level is also possible here. So therefore here n is equal to 3 bits. Only minimum number of bits possible is 3, if make more than 3 also, but here if the minimum number of bits required is 3, then only we can get the 6 levels are possible in this case. So here the sampling frequency is always twice the message signal frequency. So the message signal frequency is 30, so 2 into 30 is equal to 60 kilohertz. So always bit rate in the PCM is number of bits per sample into sampling frequency. So therefore number of bits per sample is 3 and the sampling frequency is 60 kHz. So therefore 3 into 60 is nothing but 180 kbps. So therefore we can conclude that here the unit of n is nothing but number of bits per sample, and also here the fs is called as a sampling frequency. The unit of sampling frequency is number of samples per second. So if it both get cancelled, so therefore the unit of the bit rate is number of bits per second. So therefore these many number of bits are being traveled or passed in 1 second, which is 180 kbps. So this is the correct solution of this question. So by this lecture we have successfully completed the 140 questions in a very detailed manner. And if you like the content of our channel, then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button. If any improvements needed, please do comment in the comment section. We will definitely include all those improvements in the coming lectures. Thank you so much for watching this lecture. Keep smiling, take care, and bye bye.